Sticking with the idea of polar coordinates, an obvious question is, well, how do we extend this to 3 dimensions? Many of the things that we're going to be modelling exist in 3 dimensions. How can we extend polar coordinates to 3 dimensions? One way of doing this is through what we call cylindrical polar coordinate. So let's imagine we're modelling a piston within a cylinder. We have a piston rod, end of the cylinder. Let's say we're dealing with some points A, B and C on the end of the cylinder. Now we do look at points A, B and C, and then let's imagine we have X going in this direction, Y going into the plane, but effectively, for the drawing purposes in this direction, Z going up here. Now we see that A and B have the same value of Y, B and C have the same value of X, but perhaps it's A and C that have more in common than either does with B. So it'd be useful to have a set of coordinates reflecting that fact, that A and C have more in common being on the edge than they do with B, near the middle. So cylindrical polar coordinates are actually very similar to the plane polar coordinates that we saw previously. But they do include a third coordinate, Z. So if you imagine, yes, X and Y we have in rectangular coordinates, Z perpendicular to X and Y. In cylindrical polar coordinates, we have plane polar coordinates, and then we have Z perpendicular to that. So what we have here, we can see, yes, imagine we had X and Y and Z. Let's replace X and Y with rho and phi. Now, slight change of notation here. The conventions say that we work with rho and with phi. So we have rho and phi playing the same role with respect to X and Y that in plane polar coordinates r and theta did, but we also have Z perpendicular to the plane given here. So it's good for modelling something with cylindrical symmetry. If you imagine Z points along the axis of the cylinder that we're working with, rho gives us the distance of a given point from this axis, and then phi tells us the angle involved there. So here we have it, rho, distance from the central axis, Z, position up and down, and then phi, the angle from the central axis to a particular point. But it's often easy to think of it as, yes, plane polar coordinates with a Z put on top of that, going perpendicular. Now, of course, just like in plane polar coordinates, we had equations linking the various coordinates. The same thing happens again, and effectively it's the same that link X and Y to rho and phi, that linked X and Y to r and theta in the plane polar coordinates. So we can say, remember, rho is a distance, phi is an angle, X and Y are distances, X is rho cos phi, Y is rho sin phi, and of course it's the same Z. If we're working the other way, rho is perhaps the easier one. Rho is the square root of x squared plus y squared. And then, of course, we have that if we divide the two of them here, tan phi will be y over x. And once more, perhaps the trickiest part is making sure that you get phi in the right quadrant. So here's an example. Let's imagine we start off with rho, phi, noting we're in radians, and z. How do we convert this to x, y, and z? How do we convert to Cartesian coordinates? Here we have our rho, phi, and z. Perhaps we could draw a diagram. And let's draw a diagram. We're looking straight down X and Y, let's imagine we have Z coming towards us. Now phi is 1.6 radians. That's marginally greater than pi over 2. So we have an angle here of 1.6 radians. Remember, pi over 2 is around 1.57. We're out at a distance of 2.3. Well, we have that x is equal to rho cos phi. So that would give us 2.3 times the cos of 1.6 radians. The cos of 1.6 radians is small and negative. We get around minus 0.067. Y is given by rho times sine theta. So we have 2.3 times the sine of 1.6 radians. And that gives us 2.299. We look at the results there, and of course, if it was 2.3 straight up, we'd have 2.3. It's just curved at an angle here, so we get something marginally less than 2.3 and a small negative result for x. And of course, z, it's the same z. Z remains as 3.2. So here we have the values of x, y, and z. Let's see another example, and this time we're going the other way. We start off with x, y, and z. We want to give the position using cylindrical polar coordinates. So we have our values of x, y, and z. Once more, let's draw a diagram of where we're looking at things from down the positive z axis. So if you imagine we have x and we have y, we're looking from positive z. You see that our value of z is negative, so the point would be down beneath this plane that we've drawn here. X is minus 1.9, so we go this way. Y is minus 2.3. X and y are both negative. We'll get a point somewhere near here. So this is at minus 1.9. This is at minus 2.3. We'll have our rho here. Now, ordinarily, yes, our phi would measure the angle anti-clockwise from the positive z-axis, but of course you can see we've gone past pi, so we can now imagine phi will have a negative value because the nearest way to get to this point is clockwise. So we would expect a value of rho somewhere between 2.5 and 3. It'll be a bit greater than the 2.3 units here, but not massively so. We would expect our phi to be negative, to be between minus pi over 2 and minus pi. You're somewhere near minus 2 radians. But let's use the formulae. So if we said that rho was equal to the square root of x squared plus y squared. So the square root of minus 1.9 squared plus minus 2.3 squared. Remember, when we square something negative, we get something positive. Square them, add them, take the square root. We get 2.98. Of course, I said between 2.5 and 3, it's significantly closer to 3 at 2.98. And then phi, what can we tell? We can tell that tan phi is equal to y over x. That's minus 2.3 divided by minus 1.9, which gives us 1.21, and then of course 1, 2, it's in the third quadrant. So phi is in the third quadrant here. Well, what happens when we take inverse tan of 1.21? So inverse tan of 1.21, it turns out is 0.88, working in radians. But of course, this is in the first quadrant. It should be in the third quadrant. We get it in the first quadrant. So to put it into the third quadrant, we subtract pi. Remember, if you add or subtract multiples of pi, the tan remains the same. So, to get phi in the third quadrant, subtract pi. We get that our value of phi would have our 0.88. We subtract pi, and then, at least at 2 decimal places, we get minus 2.26 radians. And of course that looks reasonable. Minus 2 radians would give us somewhere near here. We're going just that little bit more clockwise, so that little bit more negative, minus 2.26. And of course z, it's the same z. Z is minus 4.1. So what we come out with here, rho is equal to 2.98, phi is equal to minus 2.26, and z is minus 4.1. So we've found rho, phi, and z for the point here.